Okay, in this video I'm going to talk about Dwdm system basics. And at this point in the semester I think we're sort of leaving the textbook, and so, well, in any case the presentation is not firmly rooted in any particular chapter of the textbook. So what I'll do here is give you the overview of DWDM systems, and what I'll do is I'll try to make this relevant to the Cisco ONS 15454 system, and use this as a lead-in to going over some of the details of that Cisco system. The basic idea of DWDM is that we can have lots of different lasers at different wavelengths. Let's say that we have an N-channel system, and we can combine them using an optical multiplexer. Okay, and what this does is it takes a number of fibers as an input and has a single fiber as an output. And on this output fiber we have all of these wavelengths simultaneously being transmitted. Okay, and so for example, if you use and then at the other end of the line we have an optical demultiplexer which splits them out. So these are all transmitters over here, and it splits them out into a whole bunch of different receivers. Okay, and this is great because it allows you to put many different wavelengths or many different optical channels on one fiber. So we have many optical carriers on one fiber. Okay, and if, for example, you looked at the signal in this fiber using an optical spectrum analyzer, what you'll see is something like this. What you'll see is a function of, say, wavelength and optical power. You'll see a trace that looks maybe something like this, where we have more or less evenly spaced wavelengths appearing, and at least in this picture they all have the same, more or less the same optical power, and that is desirable. And so you can literally see these things, lambda 1, lambda 2, dot dot dot. And depending upon the channel spacing, you can fit more or less wavelengths within the different bands. Okay, so we have the different bands. Okay, generally speaking, we can divide WDM systems up into two types, coarse WDM and dense WDM. Here I have DWDM, so this is dense wave division multiplexing. Okay, and so in dense wave division multiplexing, generally speaking, we use the 1550 nanometer wavelength range. And that wavelength range is divided up into two different bands, the C band, and I'm just kind of going off the top of my head, more or less 1530 to 1565 nanometers, and then the L band, which is more or less 1570 to 1610 or 1615 nanometers, something like that. in any case, there's the C band and the L band. And the C band is the most traditional because that's where EDFAs work. Okay, so optical amplifiers, that should be my next slide here, and I'll give you some idea of EDFAs. So an EDFA is the erbium doped fiber amplifier. And the EDFA has a pump wavelength of 980 nanometers, and we have a section of doped fiber. So we have a section of erbium doped fiber, here, and we have an input at 15 in the C band, let's say, and then we have a 980 nanometer pump, okay, laser, and this pump laser can pump that erbium fiber, and I think in modern amps they have 980 nanometer pumps coming in from both sides, and that keeps the, you know, the 980 pump is very strong over on this side of the erbium doped fiber, but then it dies out. And so if you pump from both sides, you can keep the number of 980 photons in this erbium doped fiber quite high. And I'm not going to go into any of the details on how all of this works, but suffice it to say that a 980 nanometer photon has a higher energy than a 1550 nanometer photon, and the 980 nanometer photons can be made to lose some energy and create 1550 nanometer photons. And then we have our output. Okay, and typically 10 meters of erbium doped fiber is what we have in some sort of a coil in the device. And the EDFA has a gain spectrum that looks something like this. If I plot from, say, 1520 up to 1570 nanometers as far as wavelength goes, and I have the gain in dB here. Okay, I can get the highest gain. Let's go up to 35 and start at 0. So maybe this is 30, 20, 10. Okay, and the gain curve for the EDFA looks something like this. Okay, so we can get quite high gain, and it depends upon how much power you're getting out of it. But this is about as high of a gain as you can get. You can get up somewhere between 30 and 35 dB of gain at the peak, which is at about 1530 there. In any case, the gain is not lambda independent. And this causes a problem for WDM systems. First of all, notice that this wavelength range sort of defines that C band. C band is sort of defined for the operation. EDFAs. Okay. I think they can make L-band EDFAs also, but they're more expensive, or at least they used to be. And So this is the basic thing. So the fact that our gain is a function of wavelength is a problem, though, for these WDM systems, because what you really want is you want to have equal power in all of the channels. Okay, and so what you do along with these EDFAs is you have a bunch of you have a gain flattening filter. Okay, so it has a loss profile complementary to that of the gain spectrum. Makes the EDFA gain lambda independent. Okay, and that's an important thing because, and I'll show you in the next video a little bit, I'll talk a little bit more about it. We really do want all of our optical channels to have the same power in a WDM system. And I'll come back in the next video and continue from there. Thanks.